Welcome to Unit 4 of Linear Relations. Now throughout this unit we are going to work on patterns that could be presented in the form of a table or pictures and then represent these patterns as a linear equation. We'll also identify independent and dependent variables and then study them to determine what makes a relation linear, and we'll look at graphing linear relations, and then using the tools of interpolation and extrapolation we can estimate any unknown values. So let's start with lesson 1 on writing equations. Here we have Gregg, who is building a garden wall against his house. He buys stackable blocks and has arranged them such that the first stack only contains 2 blocks due to a water tap sticking out of his house and being in the way, but each stack after that is 3 blocks high, as shown in the diagram. We're asked to write an equation that relates the number of blocks B to the number of stacks S. So I'm going to start by writing this as a table of values so that I can easily see what the pattern is here. So I'm going to have the number of stacks and the number of blocks. So if Gregg had a garden wall that only had 1 stack, and that just means he would need 2 blocks. If his garden needed 2 stacks, he would need a total of 5 blocks. If his garden needed 3 stacks, he would need 8 blocks. And 4 stacks, he would need 11. Now if I'm trying to write an equation to relate the blocks and number of stacks here, I'm going to start by looking at the pattern between the number of blocks. So first thing you need to do is determine the value in which the number of blocks is changing. Some patterns the numbers will increase, some patterns decrease. Here we have 2 to 5, which is an increase of 3 blocks. Then to go from 2 to 3 stacks, that was also an increase of 3 blocks. And an increase of 3 between 8 and 11 here as well. So the equation I'm going to start with is B is equal to 3 times S, since it's increasing by 3 each time. So this is what I'm going to call my starting equation. I'm now going to test this equation to see if I'm correct or if I need to adjust the equation a little bit. So next step is to test your equation. And the way we test our equation is by plugging in a value from the table. So when S is 1, for example, I should get 2 blocks. When there's 1 stack, we should get 2 blocks. Let's see, B is equal to 3 times 1, which is 3. So our equation is not quite right. I only want 2 blocks and not 3. So I'm going to adjust my equation a little bit by subtracting 1. If I subtract 1, then I'll have 2, which is what I want. So I'm now going to say that my equation is 3s take away 1. But now that I have a new equation, I'm going to have to test this equation here again. This time I'm going to replace s with 2 to see if I get 5. So B is equal to 3 times 2 minus 1, which is 6 take away 1, which is 5, like we want it. You could also plug in 3 to see if you get 8, and plug in 4 to see if you get 11. But it should work for each of those values there. So that's our equation. B is equal to 3s minus 1. Now we're asked to use our equation To determine how many blocks are needed if Gregg needs to have 15 stacks to surround his flower garden. So having a linear equation to help us calculate this is much easier than me having to draw out 15 stacks of these blocks and adding them all up, or extending even the table of values, adding 3 each time. All I need to do is replace S with 15 and work it out. Now 3 times 15 is 45. If I subtract 1 from that, I get 44. So we'll answer this question here now with a statement and say that Gregg needs 44 blocks. Now this is just a little side note here. If you are asked to write an expression as opposed to an equation, you would just need to write 3s minus 1, because expressions do not have equal signs. So the equation would be b equals 3s minus 1, but the expression is just 3s minus 1. So it's like you can forget the equal sign and the other variable when you're writing the expression. All right, next example here. We have Jill, who made a pattern out of popsicle sticks. She made a bunch of row houses, and the first part wants us to draw the next diagram showing the pattern with 4 houses. So 1, 2, 3, 4. All right, and then part B wants us to write an equation that relates the number of houses to the number of popsicle sticks. So let's see, if we have just one house, we have 1, 2, 3, 4, 5, 6 popsicle sticks. If we have 2 houses, 1, 2, 3, 4, 5, 6, then 7, 8, 9, 10, 11 popsicle sticks. For 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And if you counted up the 4 houses, you'll see you'll have 21. So I'm going to start by looking at the pattern between the number of popsicle sticks. So from the first diagram to the second diagram, it increased by 5 popsicle sticks. And then it went from 11 to 16, which is another increase of 5, and 16 to 21. There's another increase of 5. So my equation that I'm going to start with is P is equal to 5n. So my starting equation, but now we need to plug in a value and see how we need to adjust it. So let's see, when n is equal to 1, we know that we should have 6 popsicle sticks. But 5 times 1 is 5. So in order to make my equation correct, I'm going to adjust it by adding 1 and saying that P is equal to 5n plus 1. Now I'm going to test this equation. So I'm going to plug in n to be 4 this time, and what I'm looking for is 21. So 5 times 4 plus 1 is 20 plus 1, which is 21. So there's your equation. P is equal to 5n plus 1. And then the last part of this question wants us to use the equation to determine how many popsicle sticks Jill would need if she wanted to make 10 houses. So we'll replace our n value with 10. And we'll see that Jill would need 51 popsicle sticks. So let's write that down. Jill needs 51 popsicle sticks. And once again, if it asked for just the expression and not the equation, the expression would be just 5n plus 1.